Introducing aPriori.
Hello and welcome to Best Practices for Holistic Design. My name is Sam Ellis and I'm an application engineer at aPriori Technologies. I started my career at Raytheon, working as a design engineer and manufacturing support engineer, helping out with both mechanical and electrical products. Then I switched over to a contract manufacturing role in the electronics component industry, where we supported customers in the aerospace, defense, and medical industries. Throughout my history with both large and small companies, I've seen holistic design incorporated and implemented in a number of different ways.
So what is holistic design? There's different answers depending on where you look. Holistic design is used in multiple different industries. Searching the web for definitions, I pulled these from articles focusing on user experience in web design, industrial design, interior design, and architecture. But there's an overarching theme across all these categories. Here's my definition. Holistic design is a framework for considering the life of a product and analyzing how decisions impact the interconnected whole. In its most basic form, holistic design seeks to answer a question. How will a design decision impact the development or use of the product? The product could be a website, a room in a house, an office, or even an entire city block. Today, I'll be concentrating on traditional manufactured products and how this approach can help avoid unwanted surprise costs. Let's start at a high level. Leadership determines there's a need for a new product. I'll assume a drill for this example. Competitors ABC and XYZ are well developed in the market, but we need to expand further into the space. The drill needs to meet certain requirements for it to be a successful product. It should have the same power system to integrate with other tools in the product line. It should be able to run at multiple speeds, and it should be less than 5 pounds so it's comfortable to use. I added a bonus requirement too, 50% less CO2 than the previous version. Along with government pressure to reduce emissions, many consumers are searching for more sustainable products. How are decisions currently made in the design process? It might be competitive analysis, annual volume requirements, or new feature needs. The conclusion is that these choices are data-driven, and that theory persists as we move down to the individual part level. The overall product segments out into individual subassemblies. One team may be in charge of the motor, another team may have design authority over the chuck system, and a third may oversee the casing. Each of these subassemblies likely has multiple parts, and each part has form-fit-function requirements that describe the identifying characteristics of a part. What are the shape, size, dimensions, and mass? How does the part interface with other parts? What action is the part designed to perform? So, when design engineers start working on their parts, these are the questions they're trying to answer, and the answers drive those early design decisions. What material am I going to make this part from? How is it going to be manufactured? What is the part structure going to look like? Often, these decisions are locked in early in the design phase without consideration for downstream impact, which can result in potential issues derived from poor design, such as too complex to manufacture at scale, high price point due to production costs, or high production costs that overshoot the target cost of the product. Studies have shown that 80% of a product's cost and environmental impact is determined in the design phase. Once a product passes through design, it becomes more difficult and more expensive to implement changes. So we want to see a lot of design iterations early in the product development. Let's take a look at a typical design lifecycle to see how this traditionally plays out. Design engineering analyzes product requirements and new market demand, and then designs concepts to meet those requirements. Cost engineering and process engineering understand the detailed manufacturing processes required to meet the design specifications. They also understand constraints to meet customer demand, such as component cost and required production capacity. Procurement and sourcing work with manufacturing to understand those requirements and then make decisions. They leverage sourcing techniques to optimize costs such as regional manufacturing and commodity management. It's a very linear process, and once design engineering finishes their portion, they generally don't see the product again unless there's an issue down the line. I'm going to expand out the view. The final goal is stable volume production, which happens at time X. After the original design is completed, process engineering and procurement work together to source a prototype. The part is reviewed, and then the design engineer may need to make some adjustments based on feedback. That revision is released, and then process engineering addresses any needed changes in the manufacturing process. Procurement then starts to source production parts. Maybe some of them are even manufactured internally. Now in volume production, there may be some additional issues that weren't discovered with the prototype. Design engineering addresses any ECOs, there are final updates to the manufacturing process and sourcing plan, and the part finally enters stable volume production. In fact, a 2019 Gartner survey found that just 55% of all product launches occurred on schedule. However, every touch point provides additional value to the product. Each iteration drives improvement, and we don't want to dilute that process. But we want to do it more efficiently. Holistic design strives to move everything left, stressing the importance of working together with other stakeholders to determine how the design can help avoid their bottlenecks. You want more iterations, but to take less time evaluating the feasibility of each one. Every decision is connected throughout the product lifecycle. Holistic design is not something that happens solely in the design department. It's a synchrony of all the company processes. The design of the product comes first, but the engineer needs to be cognizant of downstream restrictions. The current preferred supply base might have a limited set of machines, there might be a standard set of materials that are commonly used, and any number of other hidden variables. If design engineers have early visibility to these considerations, they can account for them during development. And if they don't, process engineering and procurement are going to have additional difficulties during the transition to production, which could result in extra cost, delays, and manufacturing complications. Let's get back to the drill casing, specifically the material selection. Design engineering needs to determine what the material should be. Typical decision points will be centered around feasibility questions such as functional needs, environmental restrictions, and visual requirements. However, this is just one portion of the interconnected whole. Process engineering has insights into manufacturing process, machine capability, and cycle time. Procurement tracks supplier relationships, material use, and bulk purchases. If design engineers take these other factors into consideration, transition to production will be quicker and cleaner. The goal isn't to give more work to the design engineer. It's to consider and incorporate feedback from other experts earlier in the process. When done right, holistic design sets up downstream success. Back to the material selection. Here we have nylon type 6 selected for the preliminary design. It's a good choice. Nylon 6 has high mechanical strength, high mechanical dampening ability, excellent wear resistance, good fatigue resistance. That will certainly meet the requirements for this part. But is it the best option when considering other implications? Process engineering knows they need to make at least 2 million units per year. They suggest using a glass-filled plastic which cools faster and allows for more parts per hour. Procurement and sourcing are currently purchasing high volumes of a different type of plastic. They're able to get better bulk pricing, which drives down the piece part cost. Here's a similar part analyzed in aPriori. Nylon 66 with 30% glass is a denser material. So, while the per kilogram price might be cheaper, the total material cost is actually a bit higher. But we're saving money due to the faster processing time. That results in a $180,000 annual difference between those two options. Let's review another example. Here's a simple part. Depending on the volume and use case, it could be plastic molded, could be die cast, or even machined from stock. Based on some initial data and requirements, the design engineer determined plastic molding would be the best suited process for this part. PCABS was chosen as a cheap plastic. The preliminary design meets all the needs for form, fit, and function. But can it be improved? There are some thick areas on the part that will make manufacturing difficult. The part will require significant cooling time to prevent warping or sinking, and even that may not be sufficient to avoid defects. The design engineer can use a DFM tool or consult with process engineering to determine how to optimize the design. No changes were made to the interface portions of the part, but some simple adjustments address the thickness concerns present in the preliminary design. With a minor design change, the cycle time per part dropped by over 100 seconds. Additionally, the part optimization provides sustainability benefits. The redesign consumes less CO2 for both material and process. That's all well and good, but how can this type of holistic design collaboration be implemented? There's many ways to implement the practice. This could be a structured initiative, driven from the top down and with detailed workflows and checkpoints along the product lifecycle. But that's not the only case. There's many tactics an individual contributor can employ while keeping holistic design in mind. The framework will be more effective as more teams adopt it, but let's start small and work our way up from there. The good news is that most design engineers already consider many of the holistic ideals while working on a part. Any considerations above and beyond basic form, fit, and function fall into the holistic design framework. The better acquainted a design engineer is with parallel and downstream teams, the better equipped they are to make these decisions. As designs progress through stage gates, it becomes harder and takes more time to implement any meaningful changes. If possible, try to get some preliminary feedback or thoughts from related departments prior to the first stage gate. Any design review is going to be much more impactful if you can show what considerations were made for those downstream processes. If these groups are too busy or don't want to provide input, there are plenty of other places to look. Other design engineers may have good ideas for the part structure. You can look at previous projects or designs, and they can provide insights into best practices, what worked versus what went poorly, company or team design standards, or even industry design standards, or review similar competitive products. So far, we've been looking at the part level, but holistic design becomes really powerful when it's applied to a family of parts, an assembly, or even a product line. A manager or team lead oversees multiple parts and assemblies. That means they can view the project at a macro level and receive insights across the part portfolio. By collaborating with sourcing and suppliers, they can mitigate material shortages by designing for the materials that they have good availability for. They can optimize material selection based on stock thicknesses or other parameters. They can analyze machine use and start to get an idea of what make versus buy will look like. And by thinking of the manufacturing process as well as the design, they can even try to optimize for a lower CO2 footprint. I have an example from a previous role. We were redesigning a subsystem of a large assembly. This subsystem was divided into multiple subassemblies, each with its own team managing development. With each team working on one or two PCBAs, you can imagine the total unique part count was very high. To try to combat this, we had a dedicated member from the parts engineering group who cataloged all parts considered for use. This was put together in a homegrown system, and as the bill of materials evolved, the part catalog evolved too. The part engineer was responsible for consolidating as much as possible, making sure wherever possible, same parts are used across different designs. There are multiple benefits for this effort, such as design commonality and consistency, decreased total assembly unique part count, and increased buying power for common components. This summarizes a sort of outside-in approach to holistic design. Downstream considerations are still being taken into account early, but it's driven by a third party who's not directly involved in the design. The strategy worked, but it was painful at times coordinating and maintaining the homegrown system. Dedicated collaboration tools help in this regard and put the day-to-day designer back in the driver's seat. Any tool to enable collaboration or maintain data in one location will help streamline the holistic design approach. I'm going to talk a little bit about how aPriori can help with that approach. aPriori has multiple different role-based applications where the data is connected throughout. This makes it easy for different stakeholders to review and provide feedback early in the design process. There's essentially two different ways to achieve holistic design. One, get feedback from other experts. And two, research and collect feedback yourself. The nice thing is, aPriori helps with both of these approaches. One of the reasons aPriori aligns well with the holistic design approach is that the software automatically generates relevant information across the product lifecycle. Using AP Design, the design engineer receives DFM feedback, and without any extra effort, they're receiving material, process, and cost information as well. They can use all of this data without ever having to wait for responses from experts in other departments, which enables more iterations faster. But they can also open up parts for review in AP Workspace. This application allows for users to comment on specific features or facts of the part, providing a centralized location for detailed collaboration. At a higher level, the interconnected data can be used to create multiple reports to analyze design trends and look for areas of improvement. This could be design changes themselves or considerations for downstream processes. All the reports I'm going to show here were generated with AP Analytics, making it quick and easy to go from analyzed parts to actionable highlights. Here's an example where we're looking at the annual material consumption for an assembly. Both HDPE and cold work 1020 steel have very high usage. In this case, it's important to check with procurement and sourcing to verify these materials are readily available. If not, maybe they have some similar suggestions, which engineering can then evaluate for feasibility. If we zoom in, nylon 11 30% glass and 40% glass have a much lower comparative annual use. At a minimum, design engineering should determine if these can be consolidated to either 30% or 40% glass. Maybe different teams develop those individual parts, and that's why the different materials were initially selected. But if combined, procurement will have much more purchase power, an easier time sourcing the parts, and less risk of a material mix-up. Here's a detailed breakdown of a sheet metal weldment. I'm displaying the stock thickness as well as the length and width of each part in the assembly. In an effort to simplify the number of gauges required, we can review the list to determine any outliers. Here we have two parts with a thickness of 0.31 inches. Maybe these can be increased a bit to 0.38 inches to align with those ones above them. There's just one part with a thickness of 0.19 inches. Maybe that could be increased to 1/4 inch. Finally, it might make sense to drop the thickness of the 3.13 inch parts down to 0.12 inches to align with all of those below. It's also worth checking with sourcing and procurement regarding stock thickness availability. Where do they plan to source the part? What are common gauges in that region? What stock thicknesses do our current supply base work with? Obviously, design engineering will have to determine what modifications are feasible based on the structure and the use case of the assembly. But analyses like these provide a lot of great thought points, and any simplification of the overall BOM will make procurement's job much easier. Process engineering is concerned with delivering products on time. Whether internally manufactured or sourced parts, there will be limitations based on machine time required. In this example bid package, there's a significant need for 5-axis mill time. Can design simplify some of the parts so they can be run on a 4-axis mill? If not, this is still valuable information for procurement. They need to figure out if one supplier has capacity or if they need to dual source some parts. There's a theme for all the previous examples. All those considerations are taking place early in the design phase when there's still time to adjust, plan, and prepare, which all leads to a smoother product release. Any meaningful change is going to take time to integrate into a workflow. It's easier to start smaller, individual teams versus the entire company. Don't try to make it perfect from the start. It's an evolution, not a revolution. And some closing thoughts to wrap it all up. By keeping future considerations in mind, holistic design sets you up for downstream success. aPriori provides a wealth of information which facilitates those data-driven decisions in design. And since it's an interconnected system, aPriori enables collaboration between design, costing, sourcing, and other departments. In short, aPriori makes it easy to implement a holistic design approach. Thanks for watching.
aPriori, making profitability and sustainability a reality for a better world.